becoming difficult to solve problems is quantum mechanics, and similarly electrodynamics. So suppose if we think of if you consider quantum mechanics, I wanted to know if some of you can voice with some examples what is the difficulty. Then I think I will have some idea which will help me in tuning my class. So I would be happy if one or two of you can speak on the nature of difficulty that you are facing. Okay, formalism is what Arshad says.
Sir, when we did quantum mechanics, we were not able to do it properly. So what we could, yeah.
That is fine. But what I'm asking is kind of a difficulty. If you can state, then I will.
Yeah. So most of the times, what happens is that we cannot have an intuition. We cannot have. For some subjects, we are getting an idea what we should do next. But in case of quantum mechanics, we are lacking that, and all the topics doesn't seem to be very much connected. Yeah, I mean, I learned myself. I taught myself some quantum mechanics, but still, I think there is much more that we can learn from quantum mechanics rather than just sticking to the books. And with proper guidance from someone like you, I think we could do a much more work with quantum mechanics.
Mathematics to concepts.
Yes, sir.
Okay. Any other inputs? Abhijit?
Sir, in our class, we have learned up to angular momentum, and from like partition theory and all, we haven't learned all those things. So sometimes we face problems. Okay. Suppose we have been given a problem and how to solve it. Like we can identify some parts of it, but what to do with those quantities, we don't know.
Okay, so that is because that part of the syllabus was not covered.
Yes, sir.
Okay. Any other? Mathematical formalism, notations.
Sir?
Yeah.
Sir, most of us are really beginners in quantum mechanics. And when I posted in the group, most of them were worried like whether it is competitive exam mode or really teach from the basics. So if you could explain about the basics, that would be helpful, sir.
Okay. So, anyways, that quantum mechanics is probably the most easiest subject of all the subjects that you are studying in MS. Because if you understand postulates properly, then you can solve any problem. So So I think one has to take time and then try to grasp the postulates of quantum mechanics properly. And once you understand, then the rest is only solving one problem after the other. Is only some kind of techniques in differential equations, some special functions. That's all that you require. They are additional tools that you will require in solving problems. Conceptually, I think you should have a good understanding of the postulates of quantum mechanics, the mathematical structure of quantum mechanics. So I think that is, once you understand that, then I think it becomes very easy. At least you will be able to formulate the problem easily. Solving the problem, of course, requires what is called an additional mathematical machinery. For example, if you do not know how to solve a differential equation, then you will not be able to solve it. But at least you can formulate it once you know the postulates. I think that is what some of you are calling it as formalism, or a connection of mathematics to concepts. Conceptual formalism, fundamentals, all these things mean just postulates. You have to get a good understanding of postulates of quantum mechanics.
Yeah, gravity tania.
Yeah? Jayashree?
Sir,
Yeah. Abhijit?
sir, as far as I have discussed with a lot of my friends when I was in university, I have seen that a lot of people knows about the postulates. Like I also know about the postulates, and some part I know how to use them. At that part easy, but a lot of students don't know like why do we have those postulates, and suppose I say why do we take the expectation, when to take the expectation, and that all. And you can start with those things and give us problems that we can solve by ourselves. So in that way you can do, sir.
Okay. Your critical number has reached?
Yes, sir.
Okay. Okay, so then we can start. And before I start, I just wanted to tell you that in some discussion between me and Ashlyn, we just decided this time. I do not know if this time is convenient for you people, but if it is not, if it is convenient, it's fine. If it is too inconvenient, then we can think of changing it. But if it is okay, we can try it for some weeks and then see how it goes. Okay. So anyway, let me begin. So I'm going to start with quantum mechanics. We can also do other things, but since seems to be some pressing need to understand the quantum mechanics too, so let us start with the basics of quantum mechanics. So I'm trying to do this postulates. So, what is so central to quantum mechanics is you have so I will try to write this set of postulates in terms of some numbers. Let's say okay, what do you mean by a quantum system? Quantum system can be an electron or an atom or a photon and any such elementary particles. So you call them as a quantum system. A single electron is a quantum system, an atom is a quantum system, a photon is a quantum system. Now, the moment we have a system, okay, so I will call this as a generic name. I use a generic name. I will say that it is a particle. But in quantum mechanics, there is a dichotomy that the particle is different from the particle that we know in classical physics. Then there is an associated which is given by h over t. And this relation is the famous de Broglie relation. And this is called de Broglie wavelength. So that means a particle has got a wave nature. And we also have waves like electromagnetic waves, for example. They also have a particle. Okay, this is let's say that if you have an electromagnetic wave of frequency nu, then it has got energy h nu. This is what is called quanta, and it has got a momentum h nu divided by c. Okay, so you may recall that photoelectric effect or Compton effect. These are the experiments which gave us this kind of a idea that electromagnetic waves have got a particle nature, particle has got a wave nature. So together this whole thing is called that whether you have a particle or wave, it has both nature, and this is usually called as a dual nature. So what is central to quantum mechanics is this dual nature. It has particle nature, it has a wave nature. So there was an astrophysicist by name Eddington. He gave a name which somehow did not become very famous. He gave a name for a quantum system called wavic. This is in some sense a hybrid name of both wave and particle. So I like this name. I would like to say that what we are going to consider in quantum mechanics is a system which has got a dual nature. So maybe you want to call it wave. Usually people call it particles, but can actually has both kinds of. There is something called a complementarity. Complementarity means that in a given circumstances, your system will either exhibit its wave behavior or it exhibits a particle behavior. Now you can see that if you read many books on quantum mechanics, it says that okay, this dual nature is a very enigmatic thing, and there is a lot of mystery around this dual nature that is woven mainly by the use of language, whichever language it is. So it is because of the language there is some kind of enigma or mystery that is there. For example, if you consider photoelectric effect, for example, photoelectric effect, or Compton effect. In these cases, you will see that the particle nature of light. Particle nature of light. On the other hand, if you look at double slit experiment, then you will see there's a wave nature. Similarly, if you look at Davis and Germer experiments, of electron diffraction, then you have wave nature of electron. On the other hand, if you look at experiments with cloud chambers, cloud chamber experiment, then you will see that particle tracks. So that is basically particle nature. So whether it is originally an electromagnetic wave or originally a particle, you have both natures. But nevertheless, in any given experiment, only one of the nature will be manifested, and this is what is complementarity. So wave nature and particle nature are complementary to each other. If you observe wave nature, you will not observe particle nature. But interestingly, at this point, I wanted to describe this double slit experiment in slightly more details. So let us look at double slit experiment. So let's say you have a source here. So this is source, and then there is a double slit arrangement, and there is a screen here. Screen. Now you see that when there is a light source, this you know that you have this Huygens theory. A classical theory itself will tell you that there are secondary wave trains, and then that gives rise to an interference pattern, maxima, minima, maximum. This is something which is understandable, and electrodynamics, classical electrodynamics also explains us how you get this interference pattern. I try to repeat this experiment. This was done as early as 1908 by Taylor and later by many people. So suppose let's say that we are doing this experiment with a source of 4 photons. Let's say the source is emitting photons. Photon source. And let's say this photon source is very low intense photon source, in the sense, for example, if one photon is emitted from the source, it goes and passes through the slit arrangement and goes and gets recorded on the screen. Only then the second photon will be emitted. So let's say that kind of a source we have. That means I am sending a photon by photon in the same double slit arrangement. And now you can see what happens, and this experiment has been done by many people and repeated with many different sources of photons, electrons, neutrons, etc. Suppose this is my screen, and let us see that is now the source is actually falling on the screen. Okay, so now source is perpendicular to the screen that you are seeing. So suppose if you see that the first photon is coming, and then let's say that it is getting registered here, and second photon is coming, it is getting registered here, etc. And then you send in a large number of photons, then you will see that there is some kind of a region where there are large number of photons will appear, and some regions they don't appear at all. So essentially what you see is a kind of a high intensity region and no intensity region. This is interference pattern. This is interference pattern. This is interference pattern. This experiment has been repeated by many people, and they have observed this in all cases. That means even if you do this experiment with photon by photon, that means one particle by one particle, the interference pattern emerges. Now the question is that why this interference pattern is emerging. For example, let's say when the photon is passing through, when a photon has started from the source, if it is a particle, then it will go either through the slit 1 or through slit 2. And if it is a wave, it will go through both the slits. Now the question is, if it is a particle, if it goes through one of the slits, then how does this collection of photons know that these are the preferential regions over which they have to be accumulated? So it looks like this experiment it appears as if when the photon is passing through the slits, it is passing through both the slits as a wave, but on the screen you are going to register only a click at a dot. That means it is getting registered on the screen like a particle. So this is something which is a very paradoxical thing, in the sense, in the same experiment, in one part of the experiment it appears it is behaving like a particle, and in a part of the experiment it appears it is behaving like a wave. So this experiment or experiments of this type are setting kind of the following question about this dual nature. So we can ask a question: what is this dual nature? Now you also notice one more thing. Suppose if you want to know from which of the slit this photon is going, then let's say you put a detector at one of the slits, you will know whether the photon is going through that slit or not, but then there is no interference pattern. So interference disappears. So the any attempt to know which slit the photon is going to destroy the interference. This is very important and very peculiar to quantum mechanics, that any act of observation is going to change the system irreversibly and permanently. So some understanding of this dual nature seems to be important to get some insight into the nature of this quantum phenomena. Okay. So, of course, doing mathematics of this one is straightforward. So you can define some probability or some probability amplitude for this to pass through slit 1 and some probability amplitude for this to slit 2, and then add those amplitudes and take modular square as the probability like that. Then you can show that interference comes. So mathematically there is no problem. But in quantum mechanics, there is a little gap between this mathematics and what is happening, and one has to carefully understand the nature of this gap, and that is where I think many students find it quantum mechanics to be difficult. Now, I want to present to you a view. Okay, this is just a view. It may be correct, it may not be correct. I thought about it for a long time, and I am thinking of this view, and this view is in some sense a kind of a resolution to the question that I have posed here about what is dual nature. So let me say that I will come back to this vehicle. So let me imagine that this vehicle looks like this. So you may ask me, why do I imagine like this? But I can imagine any way I like. But let me imagine it looks probably something like this. This kind of a picture you might have seen. This is generally called a wave packet sometimes. So let us say this is my vehicle. Okay, whether it is a photon or an electron, it looks like this. Okay, don't ask me what evidence I have got. I'm assuming that it looks like this. If it doesn't look like this, it may look slightly differently, but definitely there is going to be some localization, and there is going to be some wiggly behavior. So there is no loss of generality in assuming that this vehicle will look like this. So now let me say that I am trying to probe this vehicle with an experiment 1. Now in experiment 1, my length scale of the experiment, so let us say that this particular spatial extent over which these wiggles are there, okay, so let me call this as some L. Okay, so let me call this as some small L. Now let's say that in my experiment 1, the length scale of the experiment is L, which is something like some 100 times L. That means the length scale of this experiment is very big. So now imagine that so I have, let's say this is the length capital L. Now if I try to probe this particle under this length scale, then this particle will appear this vehicle will appear like this. Okay, so this is your L. Now what do you call? Do you call this a particle like registry or a wave like registry? Obviously in this length scale you will see that it is actually getting registered at some point. So you will say that in this experiment where the length scale is very large compared to the whatever vehicle size, then you will see that the particle nature gets manifested in this experiment. Now let's say that we have another experiment. We call it experiment 2, let's say. where the length scale of the experiment, L, is like, let's say, something by 10 or something like that. That is much smaller compared to the size of this vehicle. So that means you are going to have this capital L to be something like this. Then what is this? So this is L. So some tenth of that. That means you are going to have, this is much bigger, right? So you will see that these wiggles cannot be ignored in this particular case. So in this experiment, we will have wave nature. Gets manifested. Okay, wave nature gets manifested. Oh, it's like that. Like many authors say that this electron or the photon, they are they are bad, or they exhibit these different properties. Now it is easy to understand that it is a kind of a relation between the instrument length scale that you have and the inherent length scale corresponding to this vehicle that determines whether a particle nature gets manifested or a wave nature gets manifested. And this is not really a new idea, because if you read old textbooks like Eigenmaschbacher, etc., they used to have a comparison between wave optics and geometrical optics. In optics, in geometrical optics, you talk about something called rectilinear propagation of light. So light travels in a straight line. So when you draw these ray diagrams in terms of lenses, etc., you always take a scale and draw lines and use what is called paraxial approximation. All these diagrams assume the velocity. But when you do interference, diffraction, this kind of phenomena, then you will see that the wave nature of the light is important. So there also, when the length scale of these optical components that interact with the light, like lenses, mirrors, etc., when their length scale is much larger than the wavelength of light, then the rectilinear propagation is what is considered. But when the slit width and spacing between edges, etc., when they are almost of the order of wavelength of light, then the wave nature is important. So this idea is exactly same as what we used to do in optics. So this is so now if you go back to this experiment on double slit experiment, then when the photon is passing through these two slits, the spacing between the slits and slit width is such that the wave nature is important. So it is difficult for you to say from which slit it is going. In fact, it goes through both the slits, but the screen is so big in size that when it is getting registered on the screen, it gets registered like a particle, like in this case. Okay, so this is kind of a view, as I said, which is going to help us to understand as to what this dual nature is. Now, whatever is, so now you may say, okay, I believe this, I don't believe this, maybe this is correct, may not be this is correct. It doesn't matter. But what I'm trying to say is this interpretation or whatever view that I have presented, it may be correct, it may not be correct, or I don't know, I have not gone and seen what it is. This is kind of a proposal. Correct or not. What I'm going to tell you is correct, because we have to define something called the state of a quantum system. Okay, state of a vehicle. Okay, so the state of a quantum system. I'm going to first consider a simple one particle in one dimension. So we say that the state is defined. The state is a complex valued function denoted by psi of x comma t in one space one time dimension. So that is one space one time psi of x comma t. So there are two names for this. One name is called wave function. And there is a little modern name. Is called probability amplitude. You will understand why it is called probability amplitude, because its square is the probability amplitude. Now I want you to realize that you might have seen probability in many occasions in statistics, in statistical mechanics, etc. But probability amplitude as a concept you would have never seen anywhere. This is very specific to only quantum mechanics. There is no probability amplitude anywhere in any other branch of physics. So probability amplitude as a quantity will be appearing only in quantum mechanics. I think I discussed about it a little of this when I did quantum statistics function, but please note that probability amplitude is very native to quantum mechanics. It's an idea which is not there in any other subject. Now this complex valued function, so we can ask a question that why should it be complex valued? What do we mean by complex valued? That means x is a real number, t is a real number, but psi of x comma t is a complex valued function. That means there are going to be two functions, some psi r of x comma t, psi of x comma t. So this function is actually not one function, but they are two real functions. So this is the meaning of saying it is a complex valued function. So this question why is important. Okay, so we will. I would encourage you to think why, but if you don't know why, it doesn't matter. We will not be able to. We will still be able to make progress, but it is important to ask. We'll come back to this question, and I request some of you to keep track of these questions that we are posing but not answering, and remind me at a later time that we will answer these questions. So this is a complex valued function. Now, why should this be a function? Now remember, since this vehicle has got a wave behavior, so it cannot be a point. Like if you take a classical particle, you can say that in some three-dimensional space, I will put a point and say that this is the position of the particle. Now, like that, we cannot say, because there is some kind of a spatial overlap, or in some sense, there is some kind of spatial overlap that is there in this kind of a thing, right? So this has to be we have a function of space and time, a function of, so it has to be a function of x, because it is occupying some space. So it has to be some function of x and t, because it can change with time. Different shapes can appear here and so on. So that is one thing which one has to understand, that you cannot have a point, it has to be some function. Now this so this is an important postulate, and this is due to Max Born. It's called Born rule. So Born said that there is, suppose if you have psi of xt, it's a complex valued function, but then you can define something called psi star into psi into dx. So he interpreted this as probability that the particle, or I would call it as a vehicle, is there in a region dx around x at so probability that the vehicle is there, or a particle is there in a region dx around x at time t. And this is what is given by your Born interpretation of the probability. And Max Born had a from an older idea by Einstein. So he actually makes this remark in his Nobel lecture. In maybe something like 10-12 years before Max Born's interpretation of this probability, Einstein had a similar interpretation for light quanta. So Einstein asked the question that suppose let's say you have a star here, and then it is emitting light. Okay, so star is emitting light. Now you know that if you are here and let's say you have a detector here, and if you are looking at the energy of the radiation, okay, you are having a detector here, and let's say you are looking at the energy of the radiation, and classical electrodynamics tells you that energy will fall like 1 over r square, where this is r. But Einstein had a problem that because Einstein said the energy of the radiation is in terms of light quanta. Suppose if a star is emitting, let's say, suppose if star is emitting, let's say, some red quanta. That means there is a h nu. Nu is corresponding to the red light. That's what I mean by red quanta. Now, the red quanta will come as red quanta to the detector. It does not decrease in its energy and become some kind of an infrared quanta, right? So otherwise we would not have gone using this spectroscopy to find out what is there in the stars, right? So then Einstein asked a question that how do I reconcile the classical result that this energy falls like 1 over r square. So then Einstein defined something called the energy the classical energy that we have, he defined as some kind of an average energy, and this average energy is obtained as sum over probability of some h nu reaching there into h nu. Okay, so you can have different news for that matter, and so Einstein showed that this probability of this h nu, that your energy goes like 1 over r square. So this interpretation is due to Einstein, and Max Born had taken motivation from this Einstein's interpretation, and then introduced this probability as a postulate to quantum mechanics. Now, ironically, if you see Einstein, for the rest of his life, he did not believe in this probability interpretation of quantum mechanics. He used to make statements like God does not play dice and things like that. So, but ironically, he was the first person who introduced the language of probability into quantum physics, which actually gave rise to the Born interpretation for the wave function. Now we can ask some questions like this particular Born's rule gives us one thing, that suppose, let's say that we have some region. Okay, so let's say we have a physical region. Okay, so let us call that as some A comma B. Okay, which is a subset of a real line. Okay, so let us say this is our lab. Okay, so our lab has got boundary, on this side A and this side B, and we are doing some experiment in this particular lab. So that means if I ask psi of x comma t modulus square into dx and integrate this from A to B, that means this tells me this is the probability that the system is in AB at E. Now, if the system is not there in this room or in this lab, then we have no business of doing any quantum mechanics, because it has to be there in the lab at the first place. Then only you can compare theory and experiment. That means this is like total probability. So this has to be equal to 1. This has to be equal to 1. What does it mean? That means that if there are some functions for which this is not true, that means if modulus of AB mod psi square is not equal to 1, then such functions cannot be used to describe the state of the particle. So this is what you call as normalization. Normalization. That means psi of xt should be square integrable. Square integrable. What do you mean by square integrable? Square integrable means in this region A to B, this A and B can be minus infinity to plus infinity also, depending on your physical problem. So let's say psi of xt mod square dx should not be infinity, it should converge, it should be less than infinity. Suppose if it is less than infinity, let's say it converges to some number. So suppose if, let's say it is n, say, then you can define psi prime of x comma t as 1 over square root of n into psi of x comma t, okay, such that integral a to b psi prime of x comma t mod square dx is equal to 1. Then we say that we have normalized the wave function. So this is unnormalized, and this is normalized. This is normalized. Now, I want you to, at this point, inculcate this as a matter of discipline. Okay, never use unnormalized wave function or a state to do any calculation. Why I am saying this as a discipline is because in examinations, people try to trick you by giving you an and then they want you to calculate some expectation value or something like that. Then if you use unnormalized wave function as such, you will get a result which will be there in one of those 4 choices. But that will not be correct, because the correct thing is, if you find the state is unnormalized, the first thing that you have to do is to normalize the state. And you should use only normalized wave function for doing any calculation in quantum mechanics. This is a very valuable discipline that we should inculcate. Because many people don't understand this or try to emphasize this. This is treated as one of the possible misunderstanding that people have in quantum mechanics, and many examinations will try to test whether you have that misunderstanding. So if you have that misunderstanding, that will go against you. So right here, I want to give you a caution that never use unnormalized state for anything. The moment you see, the first thing that you should do is to check whether the state is normal. If it is not, normalize it and then only use that state for any other calculation. So this is a very important thing to remember. Okay, so this is one thing, and the second thing is that now you say that if your function is such that it is not square integrable, then we cannot use it for representing the state of a particle or a quantum system for that matter. So if you have set of all states, okay, so one can define something called a state space. Okay, now state space is a set of all possible states of the system. That means you can say that all possible, suppose let's say we generally in mathematics people define something called L2 A comma B. This is defined as set of all square integrable functions on this interval AB. Okay. Now we said already that your state has to be normalized, and it has to be normalized means it has to be square integrable. So definitely the state space is going to be so let us define this, let us denote this state space by this symbol H. Okay, and from here we know that this H is a subspace of this L2 of A comma B. It is a subset of this one. Okay, and what else other than square integrability it has to satisfy? Now this state has to satisfy certain other properties. For example, so it is a subset. Now your psi. So let us for the moment let us fix our so ignore T at the moment. That means you consider it a particular time. Now your psi of x has to be continuous. Okay, it has to be continuous. Now, why should it be continuous? Suppose, let's say that you have x and psi of x. So let's particularly take some x naught, and this psi, let's say, is discontinuous at this point. Okay, discontinuous at this point. Now, if you are looking at the value of psi at this point, when you are approaching from this side, it is this value. This means that you are going to have two values of probability at this point, which is rather unphysical. So, in order to avoid this kind of a situation, we require only continuous functions. Okay? So, psi of x has to be continuous. Similarly, there is another requirement that psi of x has to be single value. Single value. Single valued means This is also something like this. For every value of x, there should be only one value of psi. Okay. For example, you should not have a psi of x like this. Okay, so let's say psi of x. So let's say you should not have some psi of x like this. What is the problem with this? For example, if you take this value of x, then there are three values of psi: 1, 2, and 3. So this is not single valued. Okay, if it is not single valued, then that means again there is a ambiguity in defining the probabilities at that point. So it has to be single valued and it has to be continuous. And then for normalizability, has to be well behaved. Well behaved. Essentially, what do I mean by well behaved? Well behaved means as if x goes to plus minus infinity, then this should go to 0. Whenever your range includes these infinities, then it should go to 0. Okay, so these conditions have to be additionally satisfied. Then only it qualifies to be kind of a state space. So sometimes you will see that people try to give you some functions and ask whether which of the following function will qualify to be a wave function for a particle. So then you have to see something may, for example, let's say you have, let's say that, let's say psi of x is equal to some sine inverse x. Like this, if function is there, this is not single valued. Suppose if your psi of x is equal to e to the power x. So this is not well behaved. And third, if you have psi of x is equal to e to the minus x square, then this is satisfying all the three conditions. So this is like a valid wave function. So like that, you have the state space where the functions are square integrable, they are continuous, they are single valued, and they are well behaved. So if you have all these things, then they qualify to be the states of a given situation. In addition, based on the physical problem, there is going to be certain boundary conditions that the states must satisfy. For example, suppose let's say you have, let's say this is AB is the length of the box. Okay, so let's say let the physical system be particle in a box. Okay, and the size of the box is given by AB. This tells you that the particle cannot exist outside the box. That means if you have A, B here, let's say this is A and this is B. Now the particle cannot exist here. That means psi in this region 1 of x is equal to 0, and psi in this region 3 of x is equal to 0. Particle cannot exist there. Now whatever is the wave function here, at this point it has to be continuous. That means this has a boundary condition that psi 2. Okay, so the boundary condition is that psi 2 in the region 2. So this is my region 2. That's what I am saying. So psi 2 of x is equal to A should be equal to psi 1 at x is equal to A, which is 0, and psi 2 at x is equal to B is equal to psi3 at x is equal to b, which is also 0. That means your wave function, in addition to satisfying these three conditions and normalizability, they should also satisfy these boundary conditions. So the state space, as I told you, that this H is a set of functions which are satisfying all these properties. Let us say square integrability, integrable, and then property 1, 2, 3 that we have written, and the boundary conditions. Now these boundary conditions will be different in different problems, and depending on your physical problem, you can define the boundary conditions. All of them will define this state space. Now in quantum mechanics, you can see that this is the state space is called a Hilbert space. Hilbert space. Okay, so right now let's not worry about what a Hilbert space is. We will worry about it a little later. But Hilbert space is essentially defined as a complete inner product space. For example, L2 of AB itself is a Hilbert space. Okay, so inner space is basically a vector space. It's a vector space with an inner product defined. Okay, so right now it has got a vector space structure. So that is what is called a Hilbert space. So we will talk about. We have talked about the state a little in detail, and then we have seen that there is this kind of structure is there. The mathematical structure is there for the states. So I can pause a little bit and ask if there are some questions at this point. So is this too much of a detail, or you think we should discuss in this way? Some feedback.
This is good, sir.
Okay. So any questions?
Sir? Sir?
Yeah.
Sir, it was said that if psi is discontinuous, then we'll have two probabilities at a point.
Huh.
But probability at a point is going to be zero now, sir, because dx will be equal to 0.
Yeah.
Because we have defined Bond's interpretation to be mod square into dx. So probability at a point will always be equal to 0 now, sir, because dx will be equal to 0. So,
Yeah.
So
Yeah.
it doesn't matter whether it's continuous or discontinuous.
Yeah. Okay. So let me let me come back to that point. Okay, there is a slight technical hitch there. I'll come back to that. Any other questions?
So when you're discussing about that double slit experiment, hello. You are talking about when we send photon by photon, we end up having an interference pattern. And you said, like, is that if we, I mean, not knowing through which the slit the photon is going, is it the reason why we are seeing interference pattern in that case?
You can say that, because if you, the moment you try to obtain the information from which slit it is going, there is no interference. Okay, this is quite an important and very general feature of quantum mechanics. That is, interference and which way information are exclusive. If you get an information which way which path the photon has taken, the interference is lost. And if you want to have interference, you should not seek the information which way the photon has gone.
Okay, so one more question. The square of wave function giving the probability of finding particle in that given space, is it pre-assumed or is a general result that we are getting when we do that?
Can you ask again? I could not hear part of it.
So when we say that square of a wave function gives us the probability, is it a general output? I mean, or is it pre-assumed that it gives? How do we come up with that understanding that the square of wave function gives us the probability?
Yeah, so it is a postulate. So what do we mean by postulate? Postulate means it cannot be derived from anything else.
Yes.
Okay, it is stated. It is like an axiom, right? So it is stated, and now you have to come up with your own. You have to disprove it. That means you should come up with something which does not agree with that one, right?
Yes, sir.
So I think it is a good question to ask. Why did Max Born come to this kind of a conclusion? Of course, why this postulate is the way it is. Okay, that is some question. That is one question which we can ask. What was going through this in this context, in my opinion, is something like this. So you say that there is some kind of a wave nature. Now you can ask a question: what kind of a wave it is? Okay, so what kind of a wave it is? If you ask, now after Schrodinger's work, it was difficult to understand what kind of wave it is, because it is very different from the waves that we are familiar with. Okay, so it is not a wave in physical space. It is some kind of a wave in configuration space. And so, as I told you, in experiments with the cloud chamber, if two particles are coming in different directions, and there are particle tracks, and if they are waves of the wave type that we are familiar with, then they should actually overlap with each other. But then that is not happening. The particle tracks are going as if there is a particle collision. Okay, so these things have made it very difficult for people to understand this in any type of waves that we are familiar with. Like we are familiar with sound waves, electromagnetic waves, water waves, waves on a string. Okay, these kind of waves. But this cannot be fit into any of those categories. And more importantly, if you, for example, if you take two particles and write down Schrodinger equation, your wave function will be a function of R1 and R2, that is x1 and x2. Now, this is not a physical space, but this is called a configuration space. So this is a wave in a configuration space. So then they have more or less come to a conclusion that this wave is not a wave that we are familiar with physically. This can be at best what you can call as a mathematical wave. So then he took recourse to Einstein's probability interpretation, and then said, okay, this is called a probability wave, and hence you call this wave function as a probability amplitude. So what I am trying to say is, this is probably the train of thought that went in Max Born's mind in coming up with this postulate. So postulate is of course pre-decided.
Okay, sir.
Yeah.
Hello, sir.
Yeah.
Hello.
Yes.
Sir, energy proportional to 1 by r square. How does it come?
Where? That the photon case. Debash,
Yes, sir.
you are asking about that energy for that star case, right? Yeah. So I think this was a part of the syllabus that we did not cover in our electrodynamics. So you can show that if there is some kind of a radiation emitting from a source, the energy of radiation will fall like 1 by r square. Or if you say that energy is basically square of the electric field, and electric field will go like 1 by r for radiation, and energy will go like 1 by r square. This is a result which can be derived from the classical electrodynamics.
Okay.
Okay. So let us. Yeah.
So maximum considers quite proportional to probability, right?
Not clear. Your voice is not clear.
So maximum considers the square of wave function proportional to probability, right?
Yeah.
Did he consider the fourth of power or sixth power of the wave function?
No. Why are you expecting that he should consider them also?
So because in small classes, teachers used to say we use square of the wave function for making it positive.
Okay.
If we take a fourth power or sixth power, we will get positive, right?
Yeah, you get. See, there are two things here. One is that it is complex valued. Since it is complex valued, if you take modulus square of that, you will get a real number. Now, probability has to be a real number because that has to tell you what is the chance of finding the particle there, or what is the chance of certain property taking that value there, and things like that. So mod square will make it a real number. So that is why he interpreted this mod square as the probability of finding the particle. Okay, so let us probably continue. We'll talk about this inner product. So if you take, let's say you have psi of x, and then let's say phi of x. These two functions are there in the Hilbert space, let's say h. Then you can define phi of x, psi of x, an inner product, such that this becomes, so this is a complex number. This is a complex number. Okay, so this is exactly like the dot product in vectors. You take two vectors, so it is like a dot product in vectors, and that is why this is also called sometimes scalar product, because you get a scalar out of two functions. Okay, so now you can define this phi of x into psi of x. You have to define this one. That is, I know two functions. How do I calculate this one? So this is what we have to define. Now, one way to understand how to define this one is something like this. Supposing, let's say that you have let's say that let us think something like this. Let's say this is your x, and let's say there is a here and a b here. Let me say that I do not know these functions, but I know only the value of these functions at some discrete values of this x. Let's say that I'm doing an experiment. I will measure phi here, I will measure phi here, I will measure phi here, like this at some discrete values of x. Okay, so let's call this as x1 up to some xn, let's say. I know phi at this point, and at this point, at this point, at this point, at this point. Okay, so this is the value of phi that I know. So I am going to write, and all the functions in this h are known only with this resolution. That's my experimental resolution, or that's my computational resolution, let's say. Then that means I am going to have, I'm going to write down phi as phi 1, phi 2, etc. from phi n. This is the function. This is the value of phi that I know at different points. Similarly, I can have psi 1, psi 2, etc. psi n. So all functions I know only at these discrete values. Now at this level, I can talk about Hilbert space of vectors of this type, set of all vectors of this type. That means at this resolution, this Hilbert space is n dimensional. This is the dimension of the Hilbert space, because there are n components for each vector. Now suppose if I want to write down the inner product between these two, how do we write down the inner product? You write down phi 1 star, phi 2 star, etc. phi n star, and psi 1, psi 2, etc. psi n, which is equal to sum over j is equal to 1 to n phi j star into psi j. This is the inner product. This is basically like the dot product, right? So in the dot product, if you have vectors with the complex defined on the complex numbers, then this is how the inner product is defined. Now we can ask a question that if you take inner product of phi with itself, okay, suppose I take phi 1 star, phi 2 star, etc. Then take phi 1, phi 2, because psi can be phi itself. In which case what I will get? I will get sum over j equal to 1 to n phi j modulus square. Phi j star into phi j is phi j modulus square. Okay, so this is something which you can use this to define the magnitude of this vector. Okay, for example, magnitude of this vector can be defined as square root of this one. Okay, so this can be used to define the magnitude of vector phi. Okay. Now let us come back to this experiment and say that, okay, we have refined our experiments, and then let's say that we get more and more points in between. That means I will get a point here, a point here, a point here, such that in the limit that I get the complete function, that means how many points I will have? I will have infinitely many points. That means if you look at this particular j is equal to 1 to n phi j modulus square, in the limit n going to infinity, what will happen? See, for every j, this quantity is positive on j. This is essentially sum of infinite positive quantities. Sum of infinite positive quantities, which is essentially infinity, right? So this actually goes over to infinity for every vector. So that means all vectors have infinite length is of no good definition to determine the length of this one. So we cannot use the same definition as we used for a discrete discrete case. If you have to consider an infinite dimensional Hilbert space, we have to think of another definition. So in order to define let's say phi of x comma phi of x. Okay, we will say that this sum over j is equal to 1 to n phi j mod square. Since this is going to infinity, you multiply with a delta. Delta is this value, that is you evaluate this one in the limit n tending to infinity, also in the limit delta tending to 0. So since this factor goes to infinity, and this factor goes to 0, the product will remain finite. Okay. In this limit, this can be written as integral from a to b phi of x modulo square into dx. This delta is like dx. So this is the new definition for the inner product of this space of functions. Now this can be generalized, and then we can define inner product a function phi of x and then psi of x as integral a to b phi star of x into psi of x dx. Okay, this is so this particular this particular way of introducing an inner product is discussed in a book by R. Shankar. Okay, so you can read that in the first chapter. This way of discussing introducing the inner product was given by R. Shankar's book. So you can say that this particular way of writing the inner product is not necessarily unique. Okay, this is not a unique definition of an inner product. You could have actually defined an inner product by using some kind of a weight function here. Okay, so one can always use a weight function. So here a weight function used. That means it will be some kind of a w of x such that w of x is greater than 0 for all x in a comma b. So every choice of w of x is actually an inner product of this. So this particular inner product that I have written here corresponds to w of x being w of x being 1. Okay. So that is now you can see that this inner product has got the following properties. For example, if you take phi of x into psi of x, it will be, suppose if I interchange this one, psi of x and phi of x, now there will be one constant and two numbers are related, and one is complex conjugate of the other. This is one property. Okay. Now the other property is that if you take phi of x and then take inner product with some c1 psi 1 of x plus c2 psi 2 of x, let's say a linear combination of two functions, then this will be c1 times phi of x psi 1 of x plus c2 times phi of x into psi 2 of x. Okay, so this is basically you say that it is linear with respect to psi f. On the other hand, C1 phi 1 of x plus C2 phi 2 of x comma psi of x, we consider like this, then this is not C1, but as you can see from the definition, it is C1 star into phi 1 of x psi of x plus C2 star of phi 2 of x psi of x. Okay, so if you are calling this as kind of left function and this is a right function, just for our convenience, so let's say you call this as right function, then this is linear with respect to right function, and this is called anti-linear with respect to left function. Okay, in fact, you can define anything which satisfies these three properties. It qualifies to be an inner product of the vector space. So you have a vector space on which you can define an inner product like this, then we say that space is called an inner product space. Okay, so I think we have okay, so I will, so you can see that I started somewhere here, not here, yeah. So I started here with a quantum system, and then the whole effort in this entire section has been to describe the state of the system, what kind of state space the system is going to be. Okay, so now we can go to the second. So this will be my second. So we have discussed to some extent about the state and space. Then we talk about what are called properties. So we call them as dynamical observables. Dynamical observables are represented by linear Hermitian operators acting on the Hilbert space H. So this is our second input to the formalism. So we talk about first an operator. Okay, so operator is like a linear, like a transformation. So suppose if I have an operator A, and then it operates on psi of x. So most generally what happens is from one state to other state. So an operator is, you can mathematically say that an operator is a mapping from H to H. It will take one state in H and it will produce another state in H. This is the most general form of an operator. So it is like this is like an input state and this is an output state. So this is like input and this is output. So now you can ask a question, what is a linear operator? So linear operator has to satisfy two conditions. First condition is that if you take an operator and take some complex number alpha into psi of x, and let's say this operator acting on alpha times psi of x, this is equal to alpha times a acting on psi of x. Alpha times a acting on psi of x. So I should be able to pull out alpha. Now the second kind is a when it acts on two functions, sum of two functions, psi1 plus psi2 of x, then it is same as the result of a acting on psi1 plus a acting on psi2. If these two properties are satisfied, sometimes these two properties are written as one statement. Okay, so combined statement. Combined. You have A acting on alpha psi1 of x plus beta psi2 of x is equal to alpha times A acting on psi1 of x plus beta times A acting on psi2. Operator satisfies either these two conditions or this condition together. We call that a linear operator. So let me give you some examples that are not linear operators. I am going to define an operator by simply saying what happens to a function. Suppose if I have an operator A such that when A is acting on psi of x, it is going to take it as square root of psi of x. Suppose I have this. This is an operation, okay? Now this is not a linear operator because the moment I put alpha, I have alpha here. So I cannot pull out alpha. So this first condition is not satisfied. So this is not a linear operator. Okay, that means every function is mapped to logarithm of itself. This is also not a linear operator. Okay, so these are some examples of operators that are not linear. Other operators like differentiation, integration operators, they are linear operators. And those are the ones which we come across in our usual course. So it has to, you have a linear operator. Now we have to define something called adjoint of an operator. Adjoint of an operator. So we denote if A is an operator, you always put a cap on the operator like this. Then adjoint of A is denoted as A dagger. Adjoint of A is denoted as A dagger. pronounced as A. Okay, so you have to define this adjoint, and the definition of this adjoint is using the inner product. Suppose you have two functions, so let phi of x and psi of x be in H, any two functions in H, then phi of x, the inner product of phi of x and A acting on psi of x. Remember, A acting on psi of x will be some other function. So it's an inner product of phi and that resulting function. This is same as A dagger acting on phi of x and that inner product with psi of x. Okay, so this is kind of a definition of how we define the adjoint of an operator. Now, try to understand this. Suppose if so, let us consider so let's say consider our Hilbert space to be square integrable functions defined on the entire real line. Okay, suppose you consider like this. Then suppose I say that I have a differential operator A is equal to, let's say, d by dx. I want the adjoint of A. Okay, so you ask a question, what is A dagger? Okay, so let's go and do this. So I have to substitute this in this fashion, in this definition. So I have phi of x into d by dx of psi of x. Okay, so this is an inner product. So since this is the entire real line, I have minus infinity to plus infinity phi star of x into d by dx into psi of x dx. Now, swapping the differential operator is done by what we call integration by parts. So I'm going to choose this this as my u and this as my dv. So this is phi star of x into psi of x from minus infinity to plus infinity minus integral minus infinity to plus infinity e phi star of x by dx into psi of x dx. Now you can see that this particular term at the boundaries will go to 0 because these are well-behaved functions, and so this psi of x and phi of x, all these functions will go to 0 as x goes to plus and minus infinity. So this will become 0. As a result, I can write this as integral minus infinity to infinity. I will write this as minus d by dx acting on phi star of x into psi of x dx. This basically, if I write it again in the language of this inner product, this is like minus d phi by dx, minus d by dx into phi into psi. So phi of x into psi of x. So this, when you compare this one with the definition, Okay, so compare this with the definition. Compare with the definition, then you can immediately notice that d by dx dagger is equal to minus d. Okay, so this is yeah. Yeah,
So in the second last step, when you converted from minus d by dx of 5 star x, then you have written down in terms of the inner product. Does this means that d by dx of 5 star is equal to d5 by dx whole star?
No. See, when I do integration by parts, this this d by dx will be shifted from here to here, right? So I'm having this u is equal to 5 star of x, and dv is equal to d psi by dx into dx. So v is equal to psi, and du is equal to d phi star of x by dx into dx. Correct?
That is okay, sir. What I'm asking, sir, that if we have right in the second last step, we have written d by dx of 5 star.
Correct.
Okay. And then in the next step, we have written d by dx of 5x. So in the second last step, we can also write d by dx of 5 star x whole star.
Okay. So yeah. So I understand what you are saying. So what you are saying is that is there any difference between minus d phi star of x by dx and minus d phi of x by dx whole star? Is there any difference between these two?
Yes.
Yeah, there is no difference because x is anyway real number. X is real, only these functions are complex valued. So these two are same. So there is no difference between these.
Okay, sir.
Okay. So this is now I think we are closing under the time. So I just want to leave you with some exercises. So let me just we have discussed this this one here. Now suppose if I have a radial derivative. Suppose if A is equal to, let's say, del by del R, where R is radial coordinate in let's say sorry, in let's say spherical polar coordinates. Then if I ask you a question, what is a dagger? If some of you think that it should be minus dou by dou R, it is not correct. So when you are looking at this derivative, the functions that you have to consider are functions of radial coordinate. So that means you must take some f of r into dou by dou r into g of r into g of r, So when you try to expand this to represent this as an integral, you have two changes. One is your integral is going from 0 to infinity because this is the radial coordinate. Then you have f star of r into dou by dou r into g of r. Then the next change is the integration measure is not simply dr, but it is r square dr because we are talking about spherical polar coordinates. Suppose if you are using, let's say your r is radial coordinate in plane polar coordinates, or cylindrical coordinates, then instead of r square dr, you are going to have r dr. Okay, this is different in this particular case. So when you are doing this integration by parts, you have to be careful because this whatever is this factor that is there, this you have to combine with this one and define your u as r square into f star of r. Okay, and then when you are trying to transfer this one, then when you are in this case, like in this case, you must, since you have a dx here, you must pull out r square dr again. Okay, so r dr in this particular case. So I want you to try to find out what is the adjoint of this del by del r, both in spherical polar coordinates or in cylindrical coordinates. The other thing is, suppose if this A is let's say dou by dou theta, where this theta is polar angle in spherical polar coordinates. So for that, what you have to do, you consider some f of theta, dou by dou theta into g of theta, that will be equal to, your integration is from 0 to pi f star of theta into dou by dou theta of g of theta. Integration measure is actually sine theta d theta. Okay, so once again you have to put this sine theta with this f star of theta when you are doing integration by parts, and you try to find out the dagger of this dou by theta. Now there are sometimes people will try to ask questions of this type. What is the adjoint of dou by dou theta? What is the adjoint of dou by dou r? Because it is considered that this particular thing, d by dx dagger is minus d by dx, is considered to be a simple thing which everybody does in a preliminary course on quantum mechanics. But then from there, whether you are able to understand and work out these additional problems, where if you change the variable, you have to change the of the integration. Whether you have obtained this understanding or not is people would like to test. So that in that way, there will be some questions of this type of us. So I will stop here, so I think Arshad's question I still have not answered, so I will probably answer it next time. But if there are any other quick questions, you can ask.
Hello, sir. Hello, sir.
Yeah.
Sir, wave function entropy change எப்படி சார் இருக்கும்? இல்ல entropy change ஆகுமா?
இதுல wave functionல entropy change.
எப்படி சார் இருக்கும்? Change ஆகுமா?
See, we are not talking about entropy here because entropy is something which is related to number of particles. Then only we can talk about entropy. Here we are talking about a single particle which has both particle nature as well as wave nature. So the entropy as such is not relevant here. So we don't have to worry about entropy of the wave function.
Sir, the integration measure is due to Jacobian, or the R square comes due to Jacobian also. Does it come to Jacobian? The R square.
Yeah. So that comes through because of the Jacobian, because your dx dy z can be written in terms of r square dr sine theta d theta d phi. So when you have only radial, suppose when you integrate out theta and phi, what remains will be r square dr. Correct? So for the radial integral, we have to use that measure.
Sir?
Yeah.
Sir, you use the word integration measure. So sometimes I've heard people say like Lebesgue measure and things like that.
Yeah. So in measure theory, there are different measures. Measure length. Okay. So this integration measure is a kind of a Lebesgue measure.
Okay.
So are you understanding at this space?
Yes, sir. Yes, sir. We are.
Okay. Okay. Maybe I think one or two classes we will be able to get a hang of postulates, and once you understand postulates, then it's very easy to understand the subject.
Sir, I think if there is more problem solving, then it will be helpful for us.
If there is
more problem solving.
More problem solving, yeah. So basically, I think since there is also an opinion expressed that basics are required, so I started like this. But I think as we go along, we will also do more problems. Okay, so I think Ashley, can we close?
Yes, sir. Thank you.
Yeah. Okay.
Good night, sir.
Good night.
Thank you, sir.
Thank you, sir.
Thank you, sir. Thank you very much for agreeing to take this class.